Matt, thank you so much for joining, and I appreciate everybody coming in this morning or this afternoon, depending on where you're coming in from. Um, for those, just some housekeeping, who have attended the conferences yesterday, the workshop sessions rather, they will extend today for another day, and then tomorrow we'll be meeting on the Hopin platform for the main conference sessions, which will take place Wednesday and Thursday. So look out for an email from Hopin that will give you access to the platform, which is now live, in which all of the conference sessions will be taking place tomorrow and the day after. Now, so for this session, very happy to welcome Matt. Matt is managing partner and principal data scientist at BetaVector. So if you haven't heard of BetaVector, it's a data science consultancy. His full-time professional data work spans from computer vision to finance to education to consumer packaged goods and even politics. And he's earned, which has in part earned General Assembly's 2019 Distinguished Faculty Member of the Year award. Matt earned his master's degree in statistics from Ohio State, and he's passionate about mentoring folks in data science and tech careers. He's also volunteered with Statistics Without Borders and currently serves on their executive committee as the Marketing and Communications Director. We're lucky to have Matthew join us today, and I hope you enjoy the session. I'm sure if you have any questions, you can put them in the chat while it's going on, and I can take a look at those as he goes on throughout the session. But with that being said, Matt, I'll kick it over to you. Thank you so much.
Awesome. Thank you so much. I'm really excited to be here today and chatting with all of you. Like you mentioned, please feel free to put any questions you have in the chat. I'll keep an eye on that throughout our session today. But I don't have to do much by way of introducing myself. My name is Matt. I use he, him pronouns, and I'm excited to be chatting with you all today about missing data. I appreciate your patience with my setup here. I actually had a travel snafu, and so my friends have very graciously offered me their apartment. So not working with my usual setup. So if I'm a little bit slow, I'm just down a monitor, and so it's I appreciate your understanding with that. One of the things that I did put here was I put a note in the Zoom channel, and I'm going to put another note, or I'll copy it again. The materials for today can be found here at that link. You're welcome to take a look at that. You will have all of the materials from today, including the code that I'll be working with, the slides that I'll be doing. But feel free to just if you, as opposed to following along with your own set of slides or anything like that, feel free to use it as a reference after. Feel free to just do whatever makes you happiest now, whatever's the most productive for you. Whether you're actually following along with the slides or just sort of watching me talk or whatever. So with that said, what I'm going to do is I'm going to go ahead and share my screen here. Actually, David, would you mind allowing me to share? It looks like I don't have host sharing privileges. Okay, perfect. Thank you. So I'm going to share my screen here. So the first thing that's up is if you, this is the link to that information. So if you want to head to GitHub, github.com/Matthew Brems, all one word, all lowercase, /missing data workshop with hyphens in between those words, you can find a ton of information that we're going to go through today. At a bird's eye view, the way that it's set up is this. So we are going to go through 3 different notebooks today, labeled 00, 01, and 02, in order that we're going to go through them. There are the missing data slides, that's where we're going to spend most of our time. And then I've also got this README that contains a ton of resources here if you want to learn more and go beyond what we talk about during this session. Thinking about missing data as a field, you would be able to spend a full semester on it in graduate school and still not know everything there is to know about missing data. So today, hopefully you get a very practical introduction to it. You get some good skills and some good knowledge to take away. And also, if you want to learn more, we've got these resources here for you if you want to take a look at those. One other note that I want to make is that in addition to having these notebooks here, there's a solutions folder where everything has already been run. So if you don't have Python, or if you're not familiar with running Jupyter notebooks or anything like that, you should be able to just click on the solutions folder, see these notebooks, and you'll be able to see in those notebooks, you're going to be able to see everything completely run. But with that said, I'm going to move over to the slides, which I have here. So our talk today is good, fast, cheap, how to do data science with missing data. And one of the things that I want to, and so with that, here's a very quick kind of set of introduction about me. A lot of it is something that David has already covered, so I'm not going to regurgitate that. I work at BetaVector. I also sit on the distinguished faculty at General Assembly and on the executive board of Statistics Without Borders. I've done a ton of data science stuff throughout my career across computer vision, consumer packaged goods, education politics, and all of that. And then at the very bottom, depending on where you are in your data science journey, shall we say, people often recommend or they ask for book recommendations. So I've got 3 book recommendations at the bottom. I recommend people check out Factfulness if they're interested in data-driven thinking. Cole Nussbaumer Knaflich's book, Storytelling with Data, if you're interested in data visualization, and then breaking into data science and learning about algorithms and things like that, or more specifically, machine learning models. I recommend An Intro to Statistical Learning with Applications in R. But with that said, this is all available for you at that GitHub link if you want to take a more detailed look at that. What I'm going to do, though, is I'm just going to move on and talk about our agenda for today. So there are going to be 3 main parts of what we cover. First, we're going to cover just an introduction to missing data. Then we're going to move into specific strategies for doing data science with missing data. And you and I are going to spend a lot of our time there today. And then we're going to round this out with talking about practical considerations and warnings when you're doing data science with missing data. So at any point, as I get into this, at any point, please ask questions in the chat. I'll be monitoring that and just making sure that I, as hard as it is for these remote sessions to be interactive, I want to make sure that they're as interactive as possible. So feel free to ask questions and throw stuff out there because I want to make this maximally valuable to each of you. So how big of a problem is missing data? And that's a really tough thing for us to answer because in a practical sense, we can only see what we observe. So if I look at a data set and there's missing data in that data set, I don't see that. I notice that there's missing data, but I don't know what values, in most cases, I don't know what values are missing. So it's hard for us to quantify how big of a problem missing data is, but we can use simulated data to help us answer this question. And so at this point, I'm going to move over to the notebook and I'm going to share with everyone here. I'm going to share the link one more time. So this is the GitHub link that I'm going to be working from. And I'm going to go to the 00 interactive plot IPython notebook. So I have already forked and cloned this down. So if you are a user of Python, or if you're familiar with GitHub, you can do this. If you have Python on your computer, this will be old hat for you. If you just want to follow along, that's perfectly fine as well. So what I'm going to do is I'm going to open up this Jupyter notebook titled 00 interactive plot. I'm going to zoom in as well. So to make sure that you've got the latest versions of the packages here, you may want to delete this pound sign or this hashtag symbol just to make sure that you've got everything installed and upgraded to the most recent version. I'm not going to do that today in the interest of time. But go ahead and you can run each of these cells. We're going to import a bunch of libraries here. And I'm not going to go too far into the what each of these cells are doing. I'll give a brief explanation, but there's a lot of code here. This is something that you can examine more closely on your own. But our focus here is to be able to answer the question, how big of a challenge or how big of a problem is missing data. So I'm going to go ahead and generate some random data. I'm going to generate data about age and about income. I'm going to, in this cell, define 3 different functions that will allow us to model missingness or missing data. Again, there's a lot of code here. I'm not going to spend time going into that here. We'll talk about in more detail what these different these different modes of missingness mean in a little bit. I've got a function that's going to allow us to generate a scatter plot for us. And let's go ahead and generate that scatter plot here. So what this is doing, this scatter plot here is looking at we're going to set 10% of our observations to be missing. So for example, you can think of all of these blue dots as observations that exist in our data. And those gray dots are also observations that would exist in our data. But what you'll notice is the gray dots, I think of these as turned off. You can imagine that these are missing data points. And we can actually change this. So there is at the very bottom here, there's a plot interact function that will allow you to tweak the amount of missingness in your data. So here, for example, this is run with 80% missingness, but I can take that down to 50% missingness if I want, or 25% missingness. And you'll notice those gray and those blue dots are changing because some of them are missing and some of them are observed. And we can see that under different missingness types, again, we haven't talked about these missingness types, but you can see how much of a problem missing data can be. And so it's hard for us to see here because we don't have specific values for the slopes and the y-intercepts here. But in fact, the slopes and the y-intercepts are off pretty substantially. So here, looking at age to model income in this hypothetical scenario, our y-intercept and our slopes are off by even if our data is missing completely at random, which again, we'll talk about missing completely at random later. If we change this down to 20%, our slope and our y-intercept are off by like 80%, which is pretty substantial. Now, oftentimes we're going to be dealing with more missing data than just 20% of a given variable. For example, we'll worry, or we might have a situation where we're missing 30% or 40% or more. But here, just by missing 20%, we'll notice that the gap between our true line, the truth that we have defined in the code above, versus the line of best fit that we're seeing here, we notice that there's a significant difference between the slopes and the y-intercepts, even if visually it doesn't look like it's that substantial. So with that, you're welcome to play around with this. You're welcome to dive into the code. I'm going to move back over to our notebook here, or to our slides. And so as we move into this, we need to understand what is a realistic approach for us when we're dealing with missing data. So I've got a Venn diagram up here that's looking at good, fast, and cheap. And this is likely something that you have seen before. And if not, happy to explain it. So here, if you're doing a project, oftentimes people want it done well, want it done quickly, and want it done cheaply. But that's not always realistic. It's not always possible to have something that's done good and fast and cheap. So, and here, if we look at this Venn diagram, we would say they're dreaming. If somebody says, I need this done well, I need this done quickly, and I need this done cheaply, that's generally not possible. For example, if you say, I want a project that's done well, and I want it done more quickly, generally, it's also going to be more expensive in order to accomplish something quickly and of high quality. Alternatively, if you think about something that's done well and cheaply, that's fine, but in many cases, it's going to take time to deliver that. Or down here, fast and cheap, the overlap there means that something's done quickly, something's done cheaply. Oftentimes that's not high quality. And again, this sort of magical intersection of all 3 of these, it's unlikely that a manager or a client is going to be able to get something that is good and fast and cheap. I like to take this and apply it to missing data. So when we think about missing data here, there are a few different types of missing data, or a few different ways to think about our analysis. So do you want your analysis to be fast and cheap? Well, note that it's probably not going to be the best quality. But if you're okay with it being fast and cheap, ways that you can do this, you might drop all of your missing values, or you might try something called single imputation. We're going to talk about that later. If you want something that's good and cheap, you might use proper imputation, or you might use the pattern submodel method. We're going to talk about both of these later. And if you want your analysis to be done well and done quickly, where you don't have to spend a lot of time building up these techniques or understanding these techniques, then just gather your data in a complete manner up front. However, the challenge with that is that it's often expensive to do that. So we need to recognize the limitations there. So now that we've talked at a high level about missing data and some of the problems that it can cause, I want to move into strategies for doing data science with missing data, which is almost certainly why you're here today. We're going to break this down into 3 different groups. We're going to talk about avoiding missing data, we're going to talk about ignoring missing data, and we're going to talk about accounting for missing data. So avoiding missing data. You might say, Matt, obviously we want to avoid missing data, but what can I do about it? Oftentimes I don't have control over the data collection process. Well, it's important to talk about this because it's often cheaper in the long run for you to avoid missing data than to make guesses about how to best handle missing data. So there's a number of things that you can do in order to avoid missing data. For example, I've got here decrease burden on your respondent. An anecdote that I like to share here is that when I was living in DC, I would eat at Chipotle and I would eat at Buffalo Wild Wings very, very frequently. They were both pretty close to my house. I liked their food. It was good and it was easy to get. Well, when I would go to Chipotle, they would send me a push notification like an hour after I had been there, and they'd ask, "Hey, how was our food today?" And you would give it either a smiley face or a frowny face. And if you gave it a frowny face, they say, "Oh, I'm really sorry. What specifically did you not like?" And you can mention the temperature of the food, you can mention the taste of the food or the accuracy or portion size or whatever. And with that, that's it. Those are the only 2 questions they'll ask. And if you give a happy face, they only ask the first question. Well, now let's think about Buffalo Wild Wings. When I would go there, they would often want customer feedback as well. But when I gave them customer feedback, the way that it happened was this. I would show up, they would print out a really, really long receipt, kind of like a CVS receipt. It was very, very long. And at the bottom, they said, "Hey, go to this link, type in this 16-digit code, and fill out this questionnaire." And so, being someone who deals with data a lot, understanding how expensive it can be to get data, I'm like, sure, I'll indulge you. So I would have to go home. I would have to remember to go to my computer to type in the really long URL, to type in the 16-digit code, only to find like a 30-question questionnaire. And there was no way to submit a partial questionnaire, and some of the questions were open-ended. So thinking about those 2 things, even though Buffalo Wild Wings actually would always promise, they would always give you a free order of fries if you finished that survey, I imagine that not a ton of people are finishing that survey. I did not finish that survey, I think, ever, because that burden was so high. At every stage, there was another roadblock that I needed to get through. There was that roadblock was making sure to, when I get home, get onto my computer and type in those codes. Once I typed in those codes, seeing that it was 30 questions long, then it was seeing that some of the questions were open-ended and required me to write more than just, clicking a button. And so all of these things made it way less likely for me to give data to Buffalo Wild Wings, which I was happy to do. But that burden on your respondent is a really, really big challenge. This isn't limited to surveys. We can often think about it in the context of surveys. But if we think about something like, for example, let's say that you are working at a hospital and people come in and they need to fill out their full form when they show up. Well, if this is somebody who's been to the hospital before and you've got the ability to do an electronic tablet or something like that, maybe it auto populates with all the existing information, so that maybe they just have to change if they've moved, or they have to change some other information on there. But otherwise, so much of it is already filled out, again decreasing the burden on your respondent. If somebody's giving you information, how do you make it as easy as possible for them to do that? You might change your method of data collection. For example, you might change from an online survey to a phone call, or vice versa. Oftentimes, online surveys or in like on-app things that might be preferable to working on. That might be preferable to something else. It's important to improve accessibility. So whether you think about making sure that you're collecting data in, say, multiple languages, depending on the population that you're working on, making sure that you're not excluding certain people who may have trouble hearing or seeing or something like that. Basically, how could you improve accessibility to make it easier for more people to give you data if they're comfortable giving you that information? I think that the other things on here are fairly straightforward. Changing the timing of your survey, minimizing the length of your questionnaire, thinking about doing phone calls, for example, at 5 p.m. versus 8 p.m. versus 2 p.m., or maybe not having a 30-question questionnaire for people to need to fill out. The last note here: consider the content of your survey. Oftentimes people are very hesitant to give up information. We are in a day and age in which, as you know, people are just warier about what data they give up because we have a better understanding of how that data is used. I personally think that's a really, really good development for us. However, sometimes we are going to have certain content that we want to ask about, but it's going to be hard for us to ask about. For example, thinking about things like sexual history or income. These are things that are often valid things to study if I'm trying to figure out how to best understand or how to best mitigate the HIV crisis. Thinking about drug use or thinking about number of sexual partners might be a really, really important thing, but it's unlikely that people are just going to volunteer that information. So how can we avoid missing data in that sense? There are certain techniques that we can use. There are certain ways where maybe we consider not including that more sensitive content in a survey or in something else, but we just want to think about that in advance because it's important for us to, in many cases, avoid missing data. So moving on from avoiding missing data to ignoring missing data. When we ignore missing data, I imagine this is what many of us already do. We just put our data into our model or our machine learning, whatever. But we don't, we just leave it, we leave that missing data in there, or we just drop any observation that contains missing data. We're making an implicit assumption here, and we're assuming that the observations for which we've observed data are similar to the observations for which we're missing data. That's not always a valid assumption. Thinking back on the previous slide where I was talking about avoiding missing data, for example, thinking about the timing of your questionnaire. If you are deploying a survey and you only look between, let's say, 2 and 5 p.m. during the week, the work week, Monday through Friday, or the traditional work week, that's something where people may not respond to that. And so you need to be aware that the people who you are polling might be, or surveying or asking questions of, might be very different from the population at large. One very rough guideline that I've heard from before, and I hate giving this guideline out in general. I think that it's something that is not ideal. We often will want to avoid this, but a guideline that I've heard, and I'll share, because we as humans like rules and specific numbers that we can tie things to. A very rough guideline is that we may be okay ignoring missing data if less than 5% of our data is missing. Now, if you are doing supervised learning and you're missing a ton from your Y variable, that that's probably inadvisable. If you've got 20 variables and you're missing a ton from that Y variable, even though overall 5% of your data is missing, that might be a problem. And it might be tough to do data science there and ignore the missing data in that way. If you're missing a lot similarly from other meaningful variables, even if they're not a Y variable, but if you think that they are an important X feature in your model or in your analysis, this may also be inadvisable. For example, if you are trying to build a model and age is a really important predictor, but you're missing age for over half of the people, you may not want to do that. So ignoring missing data is also really is rife with challenges. And so I would encourage you to avoid missing data rather than ignore missing data. But sometimes if the amount of missing data is small enough, we may be more comfortable making that assumption. And now I want to move into how do we account for missing data, but I think it's helpful here for us to pause and shift our mindset a little bit. There is often this naive belief that we can just plug in the gaps in our data. And when I first learned about missing data, I thought that's what we were going to do. I thought we were just going to fill in the missing gaps. And this is known as imputation, fill in the gaps. But we have to do it in a very specific way, or we're just making up data, which broadly I think of as unethical. We just make up data. And I imagine that many of you do too. So in most cases, what we're doing is we're not fixing the data. We're learning how to cope with missing data. So you'll notice that the title of this talk was Good, Fast, Cheap, How to Do Data Science with Missing Data. And I want you to think about that. We're doing data science with missing data. It's in the presence of missing data. It's given that missing data exists because despite all of our best intentions for avoiding it, and in cases where we say we're not just going to ignore it, there's going to be missing data that exists. So how do we do data science with missing data? It's not like missing data is just this earlier step in the process that we just plug in and we fix everything and then we can go about our way the way that we generally want. So I think that it's important to call that out. And I like thinking about that shift in our mindset here before we get into talking about how to account for missing data. So we've talked about an introduction to missing data. We've talked about some strategies for doing data science with missing data, focusing on avoiding and ignoring it. But now I want to get into how do we account for missing data. Before doing that, I want to talk about unit and item missingness. So unit missingness has all of its values missing from a certain observation. So for example, index 3 here, they are missing all of their values, NAs across the board. Item missingness is where some, but not all values are missing from an observation. So we see, I like to think of this as Swiss cheese missingness, where there's some NAs, but there's also some other information in here. So unit missingness and item missingness have different strategies for how we tackle missing data. So what I want to do is I want to start by talking about how we can deal with unit missingness. And I'm going to move over to the notebook to get into that. So I'm going to go over here. I'm going to close out my last notebook. I'm going to open up this next one, 0-1 unit missingness. Danshri, there is no requirements file in the repo, and I'm sorry for that. And I should have that in there. Pablo, yes, the notebook can be found at this link. So you should be able to head there and take a look at that if you'd like. It is 0-1 unit missingness. before getting into this and giving folks a chance to catch up, one thing that I do want to mention here is that we are moving through this content significantly faster than I have in the past. Just seeing that there's no questions and all of that. If I am going too quickly, please ask questions and feel free to slow me down. Again, we've got plenty of time today, and I want to make sure that this is as helpful for you as possible. But it's also possible that we will finish this early, which is certainly fine by me if we do that. So yeah, please ask your questions. So I want to do a demo of how we might go about working with unit missingness data. Now remember, unit missingness is where we're missing all values from an observation. For example, let's say that we are, the example that I've got here is we're going to work in an HR department for a company. And we're going to do something called weight class adjustments. So I'm going to zoom in here. I'm going to go ahead and generate some data. And let's say that we have people who work in the finance department and the accounting department. And as HR individuals or human resources individuals, we want to assess how pleased are our employees. So what we do is we've got, for every person, we say on a scale of 1 to 10, how do you feel about working here? And we'll see that we've got scores here. We've got a 5, we've got a 4, we've got a 5. We've also got some missing data as well. So how do we deal with missing data in this case? So the first thing I'm going to do is let's look at the distribution of department. Again, all of this code is pre-written for you, so you shouldn't have to write anything on your own. In this case, the accounting department and the finance department are split 50-50. So the two departments are of equal size. And that's something that we might know as the HR person. We would know how many people work in each department. Next, let's look for missing values. How much information are we missing? We're not missing any information from department, and we're missing information from score for a significant number of people. Now, first off, you might be saying, Matt, this doesn't seem like unit missingness. And it is, but it isn't. So what we're doing here is, let's say you've administered a survey that says on a scale of 1 to 10, how do you feel about working here? And people have responded with a score of 1 to 10, but some people didn't submit that. Well, in this case, and in many cases, we have supplemental information about these people. So even though some people did not fill out a survey at all, and you can imagine if in addition to score, there was question 2, Q3, Q4, Q5, all the way on, you would see no data for those people who just didn't fill out the survey. But we've got that supplemental data that's just more biographical than anything else that we can use. And so we're going to use that information to our advantage here. So let's go ahead and drop our NAs. And let's look at what percent of our responses came from the accounting department. So here we can see that 77% of our responses, more than 3 out of every 4 responses came from accounting, and fewer than 1 out of every 4 responses came from the finance department. Well, this might make sense. Maybe accountants tend to, on average, just be more diligent about getting things done. Maybe finance people are more like, I don't need to do this, or I've got more important things to do, so I'm not going to fill out this HR survey, whatever you want to come up with. So there is a way we can do weight class adjustments here that will help us to weight our sample based on the true population characteristics. So what we can do is we're going to take our full sample, which includes the observed individuals and the missing individuals, and we're going to break them into subgroups based on characteristics that we know, which in this case, that's going to be the department, the accounting or the finance department. Then we're going to calculate a weight for each observation. And that weight is calculated the true percentage of people who are in group I divided by the proportion of observed values in group I. So that's going to be our weight. Then we're going to use that weight in any calculations that we want. So for example, in accounting, the weight for the accounting group, the true percentage of people in the accounting group is 50%. or 1/2. And then we're going to divide by the proportion of observed values in that group. And this code here is going to give us that 77.4% from above. So if I run this cell, the weight for each accounting vote is 64.58% or 0.6458. And I'll mention in a moment what this weight actually means. The weight for each finance vote is 2.21. What this means is that when I count up all of the responses that I get, if I want to ensure that my responses are analyzed in such a way that accounting is 50% of the vote and finance people is 50% of the vote, I can use these weights to do these calculations. So for example, if I take the number of responses from accounting and I multiply them by that weight. So instead of each accounting voice getting one vote or a vote worth a weight of 1, instead, each person's going to get a voice of about 0.645. People in finance, on the other hand, are going to get basically more than double. Their voice is going to be more than doubled when they submitted this survey, if they submitted this survey. So here, if I take the accounting weight times the number of people in the accounting department, or the number of responses I got from the accounting department, and do the same with finance, you'll notice that these are, aside from floating point arithmetic here, you'll notice that these are the same number. We've got roughly 2,768 responses from each group after applying this weighting scheme. So what we can do is I'm going to create a column that stores those weights in our data frame. And I'm going to check the counts of those just to make sure that I did this correctly. We'll notice that there's 1,250 individuals who get a weight of 2.21. So that means there were 1,250 responses from the finance team. And there were 4,286 responses from the accounting team. With all of that said and done, now let's go back to the original problem. You want to figure out how satisfied are your employees. So you calculate the raw mean or the average of your employee satisfaction score. And your employees seem to be fairly happy. We've got 5.7 out of 10, which for my money was not that great. But if we were to calculate a weighted mean of our employee satisfaction score, then instead, we get a different number. We see that that's different by 0.3, which on a scale, trying to figure things from 1 to 10, that's a pretty significant difference in my opinion. So Pablo asks, aren't we biasing the analysis by doing this? Maybe the happy people are in accounting are applying and we're just assuming that all of them are happy. Now, there are challenges with this. You're absolutely right. This is something that we should do with caution. So a couple of things. One, our goal with this sort of post weighting or this weight class adjustment is to decrease bias. What should we be concerned about? Well, as with many things in data science, when we decrease bias, we may increase variance. And this can be a really big deal. So the New York Times in 2016 published this article, and you're welcome to take a look at this. And this is also in the README. How one 19-year-old Illinois man is skewing polling averages or distorting national polling averages. So what happened in that case was there were a bunch of polls that were happening, and this one particular poll, I think it was a poll out of California, they were taking everybody and they were putting them into, rather than saying like just accounting and finance, they were putting people into these really, really, really small buckets. So it might be based on age, it might be based on income, might be based on gender, might be based on race, might be based on location, might be based on political party. So instead of just doing like one variable, accounting versus finance, here there might be a bunch of variables. So you're taking everybody and splitting them into these really, really small buckets. Well, understandably, when you're taking everybody and putting them into very small buckets, these weights might be really, really large at some point. They're going to be all over the place. So here, right now with finance, each finance person getting a weight of 2.2 votes, that to me already seems like a lot. Well, that New York Times article was talking about this one 19-year-old man from Illinois. His vote in this case was worth 30 times larger than the average vote, and it was 300 times as large as the smallest weight that anybody got, or the smallest vote that anyone got in this poll. So this one individual was an outlier and was just skewing a lot of polling averages, because when this poll was incorporated in the polling averages, it made it look like certain candidates were doing way better than other candidates because of this one individual, because they got such an outsized voice here. So we need to be cautious about this. We need to make sure that we decrease bias, but not at the not to the, not to our detriment. We don't want to increase variance too much. So oftentimes there's different guidelines that people will use. I don't have like a specific good guideline for when you should or when you shouldn't use it. Some people will say if you have weights that are above 3 or above 5 or above 10, and they'll just pick kind of an arbitrary number there, that you might be running into issues. So, and this is related to Pablo. Aren't we biasing the analysis by doing this? We want to be cautious about selection effects. Why did people respond, or why did people not respond? You're right. If all the happy people in accounting responded, then what we're going to do is we're just, that we're or only the happy people in finance, we're going to give them outsized influence in kind of the decisions that we're making. So it's important for us to be aware of why why this data is missing and all of that. Related to that, what might be a situation where we might not be able to use weight class adjustments? Well, here I'm assuming that we know the true distribution of our classes. I'm assuming that we know that 50% of our people are in accounting and 50% of our people are in finance. But if we wanted to understand, if we're looking at how many people are going to show up in the upcoming election, I don't know what the age breakdown is going to be in the upcoming election. I have to make a guess about that. Hopefully, it's an educated guess, but we know that things aren't always constant over election cycles. The 2008 election cycle in the United States saw then Senator Barack Obama get out significantly more of the Black vote. If we think about 2016 on the Democratic presidential primary side, way more young people came out because of Secretary Clinton and Senator Sanders. And so we can make educated guesses, but when a given election is anomalous or a given situation is anomalous here, we can do our best, but ultimately we may be making educated guesses about about what the if I scroll up here in this formula, what the true proportion of people is in a certain group. And then based on that of course skews our weights. So we just need to be very cautious about that. We're not always going to know the true proportion of people in a given group. So while I calculated the mean here for simplicity, there are a lot of, you can build a more sophisticated model. So if you want to build like a random forest or something like that, you can pass your vector of weights into scikit-learn when you're fitting your model if you're using Python. In R, for example, I've used weighted chi-squared to be able to calculate a chi-squared test, but after weighting different observations based on certain values. Monica asks if there's a counterpart of class adjustment for continuous data. That's a good question, and one that I frankly do not have a great answer to. But I think that I imagine, you could always discretize that continuous data. You run into the issues of what happens when you discretize anything. But I think that if you wanted to apply this, you could just bucket your continuous data into specific discrete buckets and then apply this directly if you wanted to. But I don't off the top of my head know of a weight class adjustment when you're not dealing with classes, but you're dealing with continuous values. So what I want to do is I'm going to head back here to our slides. So as we get into talking about missing, specifically, we're going to start moving into talking about item missingness. But I like to put these pieces together in a workflow, and I hope that this is helpful to you. So I start by asking myself, based on how much missing data I have, is it worth my time to try and address it? Some cases, the answer to that is yes. In some cases, the answer to that is no. Next, is it reasonable to attempt deductive imputation, which we're going to talk about here momentarily? Then, if my goal is to generate predictions or if my goal is to generate inference, then there are two different approaches that I would use depending on what my ultimate goal is. Do I want to generate predictions from a model, or am I trying to conduct inference and understand something? We'll talk about these moving forward. In order to get to that, though, we've got to talk about different types of missingness. Now, when I had the 00 notebook pulled up earlier, there were these labels that said MCAR, MAR, and NMAR. And I want to walk through these scenarios with you. So the first scenario, the first type of missing data is called missing completely at random. So let's say that I'm a grad student in a lab, and while pipetting, I knock over one of the petri dishes, and that petri dish happens to fall on the floor, and the lid comes off, and I lose further data that I would have collected from that petri dish. Over here on the right-hand side, I've got what that looks like. This is called missing completely at random. Down here at the bottom, this petri dish, there was nothing special about that petri dish that happened to be knocked over. It was just totally random, and it could have happened to any of the petri dishes. Here, we would say that the data of interest, that thing that we're interested in, is not systematically different between data that's missing and data that's observed. That's missing completely at random. Missing at random, which I'll just say, please don't shoot the messenger. I think these are terrible names. I wish that there was a better way to describe them, but I wish they were better, but it's not my fault that statisticians decided to name it this way. Missing at random, or MAR. So let's say that I work for the Department of Transportation, and there's a sensor on a toll road, the Pennsylvania Turnpike, and it counts how many cars go underneath. But it was broken, and it didn't gather information between 7 a.m. and 10 a.m. We call this missing at random because conditional on data we've observed, that data of interest isn't systematically different. Whether or not a data point is missing here depends on observed data. So for example, those time, that the times here, those are linked to when that sensor was broken. And so we could condition on this information when trying to fill in that missing data, or rather when trying to handle or work with that missing data. So what you'll notice, or what you might just naturally think of as a good strategy here, would be to say, hey, how can I go through this? How can I go into this data and fill in, say, the 9 o'clock hour? What you might do is look at other similar days at 9 a.m. and see what information has looked like in the past, and maybe calculate a simple average of that. We'll talk in a moment about why that's not an amazing thing to do, but you might be thinking about that as a strategy for dealing with this type of missingness. So we've talked about missing completely at random. We're talking about missing at random. Now the last one is called not missing at random, or NMAR. This goes back to the content of surveys, or one example goes back to the content of surveys. So I administer a survey with a question about income. Those who have lower incomes are less likely to respond to the income question. Well, we call this data not missing at random because that data of interest, the data we're interested in, they're systematically different between what we are observing and what is missing. Or put another way, whether or not a value is missing depends on the value of that thing itself, which is really, really tough. It almost feels like a chicken and egg problem where it's missing, but it's missing dependent on or contingent on something that it's contingent on, like the value of that missing thing itself. But we don't know the value of that missing thing itself. So this is unsurprisingly the most complex type of missing data to try and work with. So we see over here with incomes, we see that the lower incomes on average are dropped. Now, it's not a perfect rule. For example, 62,000 here is missing. Someone who was making 50,000 did feel comfortable sharing it. So it's not a perfect rule where the lowest incomes are missing, but this might be an example of what that would look like. So those are the three types of missingness. And I bring them up because it's important for us to think about what type of missingness we have. So there are a couple of tools that we can use to help us identify what type of missing data we have. So for example, there is something called Little's test for MCAR, or missing completely at random. And it tests the null hypothesis that data is missing completely at random versus the alternative hypothesis that your data is just missing at random. There's no empirical test that exists that will allow you to see if your data is not missing at random, which is a frustrating thing, but maybe not all that surprising, given that not missing at random is it's contingent on the data itself. So Little's test for missing completely at random is a way for you to see, does my data seem to be missing completely at random, or is it missing at random? That is contingent on variables that we've observed. Another technique that you can do or use is split your data into two data sets, one where your variable is observed and one where your variable is missing. And can you spot patterns in other variables? For example, let's say that we're looking at that income question from the last slide. We've got a bunch of data. And let's say I take my full data set and I split it into two subsets based on whether income is observed or income is missing. Then I look for patterns between those. For example, is age significantly lower among people who did not report their income? That could be a clue. And for me, that indicates that my data might be missing at random, contingent on age. Monica shares that yes, you can use the library missing no to visualize this. And missing no in Python is a very helpful library, in my opinion. And then finally, just think about the missing data process. Can you come up with a reasonable theory about how your missing data come about? Because you might be able to say, I asked a question that's about a sensitive topic, like number of sexual partners or income or something like that. It's reasonable that people might not be open to sharing that, especially if their answers are in a certain direction that we might deem societally inappropriate or something like that, or less desirable. And so based on that, people might be less willing to share their experiences or share that data with you. So can you just think about what's causing the missing data, or what are some potential sources that are causing that missing data? And can you come up with a reasonable theory about that that helps you to understand, no, this data is missing completely at random, or missing not at random, or missing at random? So at this point, I want to get into how do we account for item non-response? There are 5 different techniques that I want to walk through with you for this, starting with deductive imputation, and we'll wrap up with the pattern submodel approach. Deductive imputation, as the name may suggest, we're going to use logical rules to fill in missing values. So let's say that a survey asks a respondent, have you logged into a Facebook-owned product in the last month? The respondent says no. The survey then, in the following question, asks the respondent to select which product they've used the most in the previous month, and the person leaves that answer blank because they haven't used a product in the previous month. In this case, we can use logical rules to fill in missing values because we know the answer to that second question, even though it was blank, we know the answer to that second question must be none. So some of the things to consider here, it requires specific coding for us to do this. It's going to be based on the individual data set. It's not like there's a deductive imputation package that just automatically is going to identify all of these rules with 100% accuracy. Instead, it requires you to know your data well enough to be able to say, hey, I'm able to code up that if this column takes on a certain value, then these columns should only take on certain values as well. Related to that, it can be time consuming because you need to understand your data well enough. So you might have to study your data before you can go in and actually apply this technique. It requires no inference, which is a good thing. You don't have to make educated guesses. You're filling in logical values. And it can be used regardless of missingness type. So it doesn't matter if your data is not missing at random, or if it's missing at random, or if it's missing completely at random. It can be used regardless of missingness type. Moving on to mean, median, and mode imputation. And I imagine that this is something that you may have done in the past. So for any NA value in a given column, you can replace that NA with the mean or the median or the mode of that column. This is something that is quick. It is easy to implement. It seems super reasonable, but it can significantly distort your histogram and underestimate your variance. And if we're being honest, should only be considered if your data is missing completely at random. I want to talk about what I mean when I say underestimating variance and distorting histograms. So here, and this, you can find this in the 02 item missingness notebook. This code is in here. Up top, we've got the real histogram. On bottom, we've got the observed histogram. Observed values are in blue. And in orange are the imputed values. And if I remember correctly, we're missing 30% of our data here. So we just fill in that mean. Well, what you'll notice by filling that in is that that significantly distorts our histogram. It looks very, very different as a result of this mean imputation. So if you're missing a lot of values, like 20 or 30%, you're going to see something like this, that one bar just jut up from the rest of the histogram. Now, I should say before going on to that next slide, we are going to see a formula on the next slide. We're going to talk about standard deviation, and we're going to talk about variance. But I want to talk about why underestimating variance is a big deal. So you're going to see the formula on there. I've got words on the right-hand side that are going to show you how to, what's going on in there. I know that throwing up a slide with formulas is just, it can be a little aggressive. So I want to explain why underestimating variance is a bad thing here. So up here, I've got S equals the square root of 1 over k times the sum of, from I equals 1 to k, of each value minus its mean squared. This is the definition of standard deviation for k observed values. So let's say you've got a data set and you have k observed values in that data set. In the next line, let's say that you've got a data set where your first k observations are observed. And then let's say that you impute k plus 1 through n. You impute the rest of the data there. Well, now the definition of standard deviation, if you've got n observed values, notice I've got observed in quotes, we just swap out k for n. But what does this mean? I can rewrite this by breaking this out in terms of the first k steps, so the values that are actually observed. And then we've got plus here, the values for which, the n minus k values are going from k plus 1 up to n, the values that are imputed. Well, in this case, if I impute the mean, I've got x bar minus x bar. The mean minus the mean is just 0. 0 squared is 0. And if you sum up a bunch of zeros, that remains 0. So down below, if you simplify by removing the zeros, you've got here 1 over n times this numerator here is going to be basically what's that variability in the first k observations. But we're dividing by n here instead of dividing by k. So what that means by adding in all of those zeros is you are going to, and dividing by n, you are going to underestimate variance. Now, I want to ask you, I'm going to put this in the chat, where do we use variance or standard deviation? Go ahead and just respond there. What are some places where we use variance or standard deviation? Right. So Mohammed says to understand the distribution of our data or to understand our data distribution, yeah, standard deviation is often used to measure to give us more information about the spread of our distribution. Antonio says anomaly or outlier detection. Yeah, we absolutely use variance there when we want to understand how far outside a certain set of bounds is a given observation. Natasha says, assuming a normal distribution, we often assume a normal distribution with a certain mean and a certain standard deviation. We also, in many cases, are going to use variance or standard deviation when it comes to statistical inference. And by that, I mean confidence intervals, margins of error, hypothesis tests, p-values, and things like that. So let's say that we underestimate variance in a confidence interval. So if you were generating a confidence interval, oftentimes we say we are 95% confident that the true parameter is in between A and B. Well, if you underestimate your variance, then your confidence interval for 95% or a given level of confidence is going to get smaller because the standard deviation that you're using was smaller. So our results are going to artificially look more precise. You're going to look at that confidence interval and it's going to be narrower, which we usually think is a good thing. But that's only because we imputed the mean. If we had imputed other values, it might not do that. But by imputing the mean, we're going to see that get smaller. If you're doing a hypothesis test, your p-value will artificially get smaller. Maybe before imputing the mean, you've got a p-value of 0.06. But after imputing the mean, you've got a p-value of 0.03 because your p-value is going to look artificially more significant. But again, only because we imputed the mean. So while it's often an easy thing for us to fill in the mean, I would describe it as a fast and cheap method of imputation. It's fast, it's cheap, but it's not going to be good. And it might give you really misleading results depending on what you are doing. So underestimating variance can have pretty grave implications, in my opinion. Here, I included the histogram if you were to use mode imputation, just because here, this, in my opinion, looks pretty ridiculous, having that, the mode imputed here. Yeah, it seems like, it's kind of like the mean imputation, but just worse. So then let's talk about single regression imputation. So for single regression imputation, let's say that you train a model on the rows of data that are fully observed. So you're missing income for some people, but you've observed age and highest level of education for everyone. Well, in that case, your X values would be age and highest level of education, and your Y value would be income, and you fit a model on that data. Then you're going to generate predictions for any NA value in a given column. So for any NA value in a given column, you're just going to replace that NA with the predicted value from that model. This seems reasonable, but it's still going to distort your histogram. It's still going to underestimate your variance. And you should only consider doing it if your data is missing completely at random or missing at random. Here, this is a histogram of what that looks like. So you're going to be able to see here in that histogram, you're going to be able to see you've got this better distributed values. You still have that orange clump in the middle, but it seems to be better distributed or better spread out than what we saw earlier with the mean or the mode imputation. Here, I think that this does a good job of showing what deterministic imputation looks like. So deterministic would be what I just described, where you fit a model and you just plug in the predictions. However, random imputation is different, where you might still have that regression prediction, where you've got everything that falls on this line, but then you add randomness to that. You go ahead and you add randomness above and below that line. So instead, your data seems to be much more spread out. So you've got deterministic and random imputation here, and random seems to be better in this case. So in order for us to do proper imputation, we need to fill in missing data that takes into account our proper amount of certainty or a proper amount of uncertainty. Replacing an NA with one value is going to treat things like we know that value. So anytime you take a model and you fill in a missing value, or you take a data set and you fill in a missing value with one number, you are treating it like you have 100% certainty that that number is accurate. And that's not true. We don't have 100% confidence in that value in most cases. Deductive imputation is different. But here, the answer is that we need to impute multiple times. So what we're going to do is we're going to make a bunch of copies of our data set. We're going to use random regression imputation to generate values for each NA in each data set. And then once each of our, I'm using 10 as the example up here, data sets are complete, we'll do our final model or our final analysis on each data set. And we're going to combine the results of those models together, just like we would aggregate results in an ensemble model. Now, I want to walk through this with you in a little bit more detail. So let's say that you've got a data set here. I took a poor screenshot of Google Sheets here, but with all of those red values are X'd out, those are missing values. And I should say, to give credit where credit is due before this, I took this diagram and I've adapted it to break it down into something that might make a little bit more sense for us. But I was heavily influenced by that diagram. I wanted to make something that was a little bit bigger and better for slides. So what I'm going to do is step one, I'm going to make copies of this data set. So in this example here, because of the space on my screen, I made 3 copies of that data set. Once I made those 3 copies, I'm then going to build my model for imputing. So notice that nothing's changed here, but I'm going to build a model for imputation. And what that is I'm going to look at each of these data sets and I'm going to build a model. They're all the same data set, so I just have to build one model there. But I'm going to build a model that I'm going to use to then fill in those missing values. Then I'm going to impute those values properly. So notice here that in each of these copies, I've filled in missing values, but notice that they were filled in with random numbers. These should be numbers from a model that you create. For example, let's say you fit a linear regression model to the observed data in this data set. Then you're using that to fill in each of those X's. So you can do that here. And notice that, for example, this 5, it's a 5 in this data set, it's a 6 in this data set, and it's a 7 in that data set. All of these values are imputed with a random error, because if I go back here, we know that if we just fill everything in with that best guess, that we're going to distort our histogram. It's going to look kind of like this. Everything's going to be clumped together. But instead, we want to be able to better reflect the spread that is actually in our data and the uncertainty that we actually feel in our data. So you're going to make copies of your data set. You're going to build a model for imputation. And then MSing asks the question, in this approach, we're using the same model, but with random errors. You should definitely use random errors. Yes, you may be using the same model. Now, you may, in some situations, people recommend creating a new model that includes randomness even in the model itself. So for example, if you were building a line of best fit, rather than just using the same, and let's keep it simple, let's say it's y equals beta naught plus beta 1 times x. You might use random beta naughts and beta 1s that are kind of sampled from your data, but they might not be the exact same model. For simplicity, you can use the exact same model with the random errors, but that's up to you if you want to do that. I think that's probably the random selection of those beta values is probably best and most rigorously true, but also is especially time consuming and is something, as we're going to talk about with the pattern submodel method, that may just be more preferred anyway. But the short answer is that you could use the same model with random errors. Yes, you could also use slightly different models that also incorporate random errors. Yes. So we've imputed those values here. Then what we want to do is we want to do our final analysis on each of these data sets. So let's say our goal was to fit a line of or a linear regression model to this. And I use linear regression models because this, missing data was largely studied in statistics. It's something that is tangible for all of us. But your final analysis here doesn't have to be a line of best fit. It could be a linear regression model. It could be like a logistic regression model if you want. It could be a random forest, a simple decision tree, could be a support vector machine, whatever you want. But it is easiest for me to write out here these different models. So notice that I've got three similar looking models, but there's going to be a different beta naught, beta 1, beta 2 for each of these data sets. So I call these gamma and delta, not because there's anything special about them, but just to be very clear that it's not just beta naught, the same, all the way down. You're going to get different values for this y-intercept, which we're calling beta naught, and this y-intercept, which is gamma naught, and this y-intercept, which is delta naught. So you're going to build your final model on all of those data sets. Then once you do that, then we're going to combine those results together. And there's a couple of ways that you can do that. If you're generating predictions, you could just average your predictions together in a regression problem, or you can select the plurality or the likeliest class in a classification problem. So that's really similar to when you think about scaling up from one decision tree to bagged decision trees or a random forest. If I go back, you would generate one set of predictions from this model, one set of predictions from that model, one set of predictions from that model. Then for each observation, you would just average those three y hats or those y predictions together. So similar to what you would do with one decision tree versus a random forest, where with a random forest, you've got a bunch of individual decision trees and then you average those predictions together. Now that often happens under the hood, but here that's something that you could manually do here with this. If your goal isn't to do predictions, but if your goal is to do inference, so let's say you want to understand how to get a slope and get one slope and one y-intercept, because reasonably we know that we can't have 3 different models like we saw in the previous slide or 10 different models. That it feels like that would be chaos for other people. We probably need to have one model that we can give to them. And so if we're doing inference, there's a way for you to combine those estimates together. I've got details in the repository, but I don't have the details here in the slides because I feel like that goes too into the weeds for what we want to talk about today. But Rubin's rules will allow you to combine the slopes and the y-intercepts together from each model. So if I go back here, for example, you've got beta naught, gamma naught, and delta naught as 3 different y-intercepts. What you can do is you can average those together to get kind of your global y-intercept. And you can also combine, if you've got the standard error or the standard deviation for beta naught and for gamma naught and for delta naught, there's a way to combine those together. And if I go back here to what inspired this, it might be difficult to see, but they've got this down here in this diagram where you've got parameter estimates, beta 1, beta 2, beta 3 on each of these data sets, as well as the standard errors for those. And then these arrows represent using Rubin's rules to combine those estimates together so that you've got beta 1 is your average beta 1 value is 1.2, even though none of these were actually 1.2. And you can combine your standard errors together. You can get p-values and understand the significance of individual features by using Rubin's, I'll go back here so that you can see it, Rubin's rules. So you're able to do that. If you're generating predictions, you can average those predictions together, select the plurality class. If you want to do inference, you can do inference as well. I'm going to skip over the notebook here, but we can return to that later if we would like. I want to, just given that we're sort of in a groove talking about item non-response. So we've gone through those first 4 bullets. We've talked about deductive imputation, mean, median, and mode imputation, single regression imputation, and proper imputation. But the pattern submodel approach is the last approach that I want to talk about here. And so I think it's helpful to talk about this from a big picture point of view. What we're going to do is we're going to break our data set into subsets based on missingness pattern. And then we're going to build one model on each subset. We're going to create many different models here. So for example, I've got this data set where we've got Y, X1, and X2. And my first step, I'm going to split this into subsets based on missingness pattern. So all of the rows where Y and X1 and X2 are observed, I've got those together. The rows where Y and X1 are observed, but not X2, I've grouped those together. Same with Y and X2, but not X1, and same with Y. Then once I've split my data set up into these subsets, then I'm going to build a model on each subset, creating many different models. So here, I'm going to fit a model to these observations. Hopefully you've got more than 2. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Then I'm going to build my second model, which here, notice that since I don't have x2, I'm not going to fit anything to x2. Instead, I'll have y equals gamma naught plus gamma 1 x1. Again, I'm just showing you here that by using gamma here and beta, I just want to show that these are different parameter values. But there's nothing special about beta versus gamma versus delta. If I fit my next model, I'm going to get y equals delta naught plus delta 1 x2. That looks a little funky because we've got delta 1 times x2. But here we don't have any x1 values. We just have x2. And then down below, y equals epsilon naught. It's just like a y-intercept because we don't have any x feature values that we can use here. So in this case, you would actually create 4 different models. And that would be it. You wouldn't actually combine these models together like we did, like we talked about with the proper imputation approach. We would just keep these models as is, and we would save all 4 of them, or all 10 of them, or however many you generate. So there's some advantages and disadvantages to that. One disadvantage, obviously, is you now have to keep track of many different models. But there's a lot of benefits that I think are important. If your data are not missing at random, the pattern submodel method tends to outperform imputation methods. Again, imputation where you fill in missing values. If your data are missing completely at random or missing at random, then the pattern submodel method is expected to perform as well as imputation methods. Next, and this is the coolest thing in my opinion, it doesn't require missingness assumptions. You don't need to assume that your data are missing completely at random or missing at random or not missing at random. It doesn't require any of that because you're not filling anything in. So you don't have to make assumptions about that. a kicker here is that you can generate predictions for test observations that contain missing data. So let's say you gather a new piece of information, a new data point, and you want to generate predictions for that. But let's say that observation that you got actually has its own missing values in it. Like you got a new survey and certain answers are missing. Well, the way that you would generate predictions for that is if I go back to the previous slide, you're just going to match that missing observation to, or that new observation to a specific pattern here and use the model that's associated with that pattern. That's all that you would do. So you don't need to worry about, using other approaches that we talked about earlier. You would have to take that observation that had some missing values, make a guess about how to fill in those values, then generate predictions for it. But with this pattern submodel approach, you don't have to. The other downside, so I mentioned that we've got a bunch of different models that we have to keep track of. The other downside is that it's not a well understood method for inference. So if you want to do inference, I generally recommend that you stick with the proper imputation approaches. So again, pulling all of these pieces together in one workflow. So start by saying, I want to see how much missing data I have and is it worth it for me to try and address it? Next, is it reasonable to attempt deductive imputation? Can I fill in values using logic and rules that I understand from my data set? Then, if I want to generate predictions, I go with that pattern submodel approach. If I want to conduct inference, then I'm going to use the best imputation method available. And if I'm using proper imputation, which we should, then I'm going to combine my output and my results using Rubin's rules. So this is the workflow that I personally find works. Your mileage may vary, but this is what I think makes a lot of sense to me. So we've gone through the intro to missing data. We've talked about a bunch of strategies for doing data science with missing data. And now we're going to move into some practical considerations and warnings. So first, if you just want to fill in your missing values, so you've got a complete data set, be really careful about that. Because once you fill in those missing values, nobody's going to know what was actually truly observed data and what was imputed data. You could create a copy of your data set where you show like the original source information, or you could have like an indicator data set that has ones if they were imputed and zeros if they were observed, or vice versa. But realistically, after you construct that data set, it's going to be very, very difficult for people to know what was observed versus what was imputed. And just like with your code, if you leave that data set, you go on vacation or you put it down for a couple of weeks or a couple of months, and then you come back to it later, you might mistake imputed data for observed data. So you need to be, you need to be cautious of that. My second warning, improper imputation is making up data. I believe this is an unethical thing to do, so I would encourage you to avoid doing this. I recognize that there are time limitations and all of that. Sometimes you got to fill in the mean and move on with your day. I want that to be as few times as possible. So I would just encourage you to think about it through that lens. We recognize that making up data in general is not ethical. When it comes to missing data, we often feel like we take more liberties with that, and I've done that too. That's not a sanctimonious thing. I've done that too, but I would encourage you to avoid doing that. Proper imputation, for example, creating those different models with the random errors and filling in those missing values, that's not making up data because it's imputing data while properly estimating the amount of variance in your data. If I go back, the way to think about this, in my opinion, is we've got our different data sets here, and I don't know what this X is, this value should be, but I'm like, well, what if it's 5? And what if it's 6? And what if it's 7? And I've built a model that that takes that into account, because one model assumes it's 5, one model assumes it's 6, one model assumes it's 7, and then I combine those together. So I'm constructing these models assuming the right amount of variability in these values, the proper amount of variance in our data. So that is not making up data. we're properly estimating the amount of variance that we have in our data. And then my final warning here is that there are specific methods that are new-ish. Single imputer, iterative imputer, that was recently experimental. So I would just encourage you to proceed with caution. In R, the mice package, and I'll type that in here, mice, multiple imputation by chained equations. That is a package in R. That you can use for multiple imputation. But yeah, in scikit-learn, iterative imputer and single imputer. Single imputer is fine in that I think it works pretty well, though single imputer is making up data. So personally recommend you avoid those. Iterative imputer, which I believe I believe it's the mice algorithm, or the algorithm that's underlying mice. I think that has been implemented in scikit-learn under iterative imputer. However, recently experimental, so just proceed with caution. Don't just assume that it automatically works. And so with all of that, what is a realistic approach for us? So we can come up with, in this case, we can do a fast and cheap analysis. We can do a good and cheap analysis. We can do a good and fast analysis. And it's up to you what you choose to do. I think that we probably, before today, we're doing a lot of the fast and cheap analyses. And that's not said with judgment, but that's just a thing like dropping all of our rows containing missing data or filling in the mean or the median. That might have just seemed like a reasonable thing for us to do. But it's actually not a super reasonable thing for us to do. And so we want to be cautious there. A good and cheap analysis. So in this case, if you do proper imputation or you do that pattern submodel approach, that will get you to an analysis that is good and done cheaply. It will take time, especially the first couple of times you do it. It's going to be an investment of time, but you could do that. And then a good and fast analysis. If you want your analysis to be good and fast, then just try gathering data in a complete manner up front. That's often expensive. It's often hard to convince people to do that. But it often will be better for you in the long run if you can just gather your data in a complete manner up front. So that's what I've got. There weren't a ton of questions, and so I hope that that's okay. We went significantly faster than I have in the past, but I think that we covered everything and we were able to talk about stuff. But I'm happy to pause here, and I'm very happy to answer questions that you have. I want to know what questions you've got, what are things that you're thinking about, and how can I help you? I've got the chat and everything pulled up, so feel free to do that. Yeah, I'm happy to paste the GitHub link. Yeah, so that people were coming in and out. So yeah, feel free to take a look at the GitHub link, and that should have everything in there. Thank you, Nigel. I appreciate it. Brickster, yes. So we talked about item missingness. I would, and I may have done a poor job of describing that when we got to it. I'm going to flip back a few slides, so I apologize for the quick. So this is when we've got item non-response or item missingness, these 5 techniques would be techniques that you would use for item missingness. Yes. Dan Shree, is it okay to shoot more questions over Twitter or as issues on GitHub? You're welcome to do that. I can't promise a speedy turnaround or anything like that, but you're welcome to, please feel free to reach out to me. And that's why I'm gonna skip back here to the end just so people have that information. But yeah, you are welcome to reach out to me, and then I will, pending work and other obligations, will do my best to get back to you as quickly as I can. Mohammed, how about we use KNN imputation? What do you think about it? I think that KNN imputation is an okay thing, much like it's more sophisticated than mean or median or mode imputation. I think of it as on the same level as like a single regression imputation. I think that it's okay, but you're still going to fall prey to the issues um, of of single imputation in general. Now, if you're doing multiple imputation using KNN, then I think it's more sophisticated. But to my knowledge, KNN is I've only seen a single imputation implementation of KNN imputation. So I think that it's about as good as single regression imputation would be, and is going to fall prey to a lot of the same things. It'll be better than like mean or median imputation, but it's still going to fall prey to issues, and you would probably be better off doing the pattern submodel approach or proper imputation. Julia, when you input with random error, would it still ignore possible complex relationships with the other variables? For example, a range of missing values that is not completely random? Yes. So you have to be cognizant of what errors you use. So if I go back here, when you've got you've got these data sets and you've imputed these and there's random errors there, yes, you need to take care to include the relationships among variables when imputing them. You may not just want to do a totally stochastic or totally random value to put in there. There are certain implementations. I believe that mice, that multiple imputation bi-chained equations, I believe that that takes it into account. It's an iterative algorithm that sort of converges to the maximum likelihood estimates of the data, if I remember correctly. And there's a Bayesian implementation as well. But yes, I think that it's important to include those other sources of error. Natasha, the first step to make the multiple model imputation. So if you're doing proper imputation, I would start by making copies of your data set, then build your model or your models for imputing to fill in those values. Then you would fill in the values, generating predictions with some random error, maybe correlated among variables, and then do your final analysis on each of those data sets. Then you're going to combine those values together, much like you might combine the estimates from multiple decision trees when doing a random forest or something like that. Amar, once the model is deployed, is there a metric for what percentage of missing features you would accept? I mean, as close to zero as possible. I would, so the very rough guide that I gave earlier is that if you've got 5% or less of your data that's missing, then I might be okay ignoring that missing data. But that is a very rough guideline. I think that it depends on what values or what variables are missing. I mean, again, if you're missing 50% of your Y variable, even if it's less than 5% of your overall data set, you're probably going to run into all sorts of issues. So I don't know that I would ignore it there. I would try and there's a lot of different things that I might try there. So yeah, I think that 5% is a very rough guideline, and I would still proceed with caution. Nigel, would you suggest that the pattern submodel approach can be a successful part of EDA or exploratory data analysis prior to model development? That's an interesting question. I think that even if you don't actually build the models themselves, the submodels, I do think that would be an interesting approach to EDA. So what I mean by that is again, I apologize for all of the skimming back and forth. But if you were to split your data set into subsets, it might just be really interesting to see what happens among this top subset or in the next subset and so on and so forth. That might be an interesting thing to check out and see and better understand. Like, hey, is this like, are there interesting patterns that we can pick up based on the missingness here, even before we fit any sort of model? Antonio, is it possible to mix proper imputation and the pattern submodel approach with high dimensional data to prevent an unmanageable number of submodels? That's a good question. In both cases, you're creating multiple models. I think that I have never tried to mix those two approaches. I feel like it would be an interesting exercise to try working with those multiple approaches. One thing that I would encourage you to do, so an unmanageable amount of submodels may be valid. So if you've got k features in your data set, then you can have up to 2 to the k power missingness patterns. In practice, it's usually going to be far, far lower than that. I would recommend, rather than trying to mix two different methods, because I don't know how those would work, Antonio, what I would recommend is, are there ways to collapse classes together? So, for example, this is maybe not the greatest option here, but what you could do is you could, for example, with these values and these values, you could just pretend that X2 doesn't exist here and just collapse those top two sections or segments together so that you've only got one model there instead of two. So if you think that's something feasible, you might try and do that. But I would be interested to know first, like, how many submodels you have, and then you can make that decision there. Hey, is this too much, and do I need to come up with a clever solution to that? Let's see. So got a DM. I'm curious. I've dealt with missing data where the missing data had features like autocorrelation in time series. To be more specific, like in the features includes autocorrelation in CPU usage data. What can be the best approach here? That kind of gets back to that same question of, if you're doing multiple imputation and thinking about those errors when you're filling in these values here, you might say, hey, I want to incorporate that autocorrelation in the error component, or fill that information in. And that might be an interesting thing. For example, if I go back to the example of missing at random here, where the number of vehicles are correlated over time, and you're going to see a seasonal pattern happening probably 5 days a week. So I think that, yeah, I would incorporate that. If you're doing proper imputation, I would incorporate that when doing this component and making sure that those values are imputed respecting the true correlation structure of the data. Do you have additional tips for when you do have missing values on your Y variable? I wish that I did. I I don't have a great answer. I think that, I would consider looking at unsupervised approaches and see if that just makes sense. I would certainly try to impute those values and see if I can get those values elsewhere. But I would consider converting to an unsupervised learning problem, or trying to fill in values, or maybe come up with a proxy for my Y variable. But nothing like specific to like missing data here. I feel like there are going to be strategies that you've likely already considered. Dantry, I want to circle back to Amar's question. Typing in Vim, that's totally okay. I think the question was about real-time prediction and possibly production environments for a deployed model. If there's item missingness in an incoming request, how should that be dealt with? Should there be a pre-processing step that checks if the request has only as many features as missing or as acceptable? Yeah, so if you, and assuming that I'm understanding this correctly, I think that I might try to do the pattern submodel approach, because there, even if you've got a value that has no features observed, there's still a model that you can build. You can just do the y-intercept of those values. So I don't think that there's a limit to the number of missing features that I might accept in that case. And I think that yeah, I think that I would probably choose to start with sorry, I might start with the pattern submodel approach. So I would, because this just naturally is set up to handle situations where, if incoming features do have anything missing, you don't have to compromise your analysis for that, or you don't have to fill in those missing features, or you don't have to say, well, this is irretrievable, so I'm going to get rid of it. You can just kind of deal with all of it here in that pattern submodel approach. I don't know if that addressed your question, Dantry, or Amar's question from earlier, but I hope it was helpful. All If there are any other questions, please drop them in the chat. I don't see any other questions right now, so I'll give folks a moment to do that. But I will take this opportunity while people are potentially typing to just thank you again for your time and attention. I appreciate you taking time out of your, I guess, is it Tuesday? Yeah, time out of your Tuesday to learn about missing data. So very excited to connect and discuss things moving forward. But thank you all very much. I see David's come on, so I'll let David chat.
And I just wanted to thank you, Matt. It's been very helpful, very informative, and this was a great session. So I'm very grateful to have you. I hope we can have you back again. And for those who are participating in this session, we'll also be sending the video out afterwards, as well as some of the links that Matt was kind to drop in. So yeah, I hope if you're attending more sessions this afternoon, you enjoy those. And tomorrow and the day after, we'll see you on the Hopin platform for the main conference sessions. Just a reminder to please check the email for the Hopin link to join. That's now open, so you should receive that. And please thank Matt for taking the time. It was great. I hope you found it helpful. I certainly did. Thank you so much, Matt.
Yeah, thank you. It's good to connect. So
You as well.
thank you all, everyone. Take care.
Bye now.